Okay, good morning. Good morning and welcome to everything you ever wanted to know about SIMBA. Thanks for joining us today in this webinar dedicated to power electronic simulation. I'm your host, Emmanuel Ritovic, and I'm the founder of AESIM, the company behind SIMBA. I have the pleasure to have with me Guillaume. Guillaume, would you like to introduce yourself?
Yeah, thank you, Emmanuel. My name is Guillaume Fontes, and I'm an associate professor at the Toulouse National Polytechnic Institute, specialized in power electronics. And now I'm joined the SIMBA team a few weeks ago, and it's a pleasure to participate to this webinar.
Awesome. Just a few words about AESIM. AESIM is a Canadian startup. We are based here in Montreal. We provide electrical engineering consulting services, and we develop simulation software. We've just released SIMBA, our first product, just a couple of weeks ago. I wanted to give you a little bit of background about SIMBA and how we actually started this project. Uh, I started to think and to develop SIMBA more than 10 years ago when I was actually a student at the university and Guillaume was one of my professors. At that time, we were using simulation tools for projects and to learn power electronics. And I actually didn't really like the tool. I found them a little bit slow and not very powerful and not very modern. So I started to think about a new platform. I actually found very recently in one of my notebook a draft, a prototype of a UI that I was designing. And this notebook actually is about 10 years old. So I just wanted to show you how old actually this project is and how long we've been maturing it. So then after that, I've been working in the industry as a power electronics engineer and as a power system engineer. And in 2018, almost 3 years ago, I decided to leave my job and to start a company um, and to focus on the development of SIMBA. About a year after I started a first beta version, I released the first beta version of SIMBA. We had about 50 users, and one of the users was actually Guillaume, and we started to work together, and we decided it was a very good idea to become a partner on this project. We then released the public beta of the software, and this was a huge success. We had about 300 users all over the world, both academic and people from the industry, and that was amazing. We had feedback, people that I never met, they made feedback with made report of 10 pages long about how to improve SIMBA, what should be, what are the weaknesses, what are the strengths, and that was very helpful to build the best possible simulation tool. And once we were sure that the solver was accurate for every type of converters, whatever its size, whatever the type of converter, we decided to release SIMBA. And that was just a couple of weeks ago. Um, Somebody comment that the sound is bad. Is the sound okay? Somebody is complaining about the sound quality. Maybe let me know if it's better now, please. I will continue, but let me know if the sound is better. I apologize about this technical issue. Do you still have noise and echo? Echo and some noise. Better. Okay, so I will continue like this. Sorry about that. It's the first time we do a YouTube stream, so we have to learn. Okay, it's great. Awesome. Thank you so much, and sorry about that. So we decided to release SIMBA about 2 weeks ago. So in the end, what is SIMBA? So first, SIMBA is a new power electronics simulation tool aiming to simulate any type of power converters with unprecedented speed and simplicity. The more long-term vision is to build SIMBA as a platform dedicated to unlock real innovations in power electronics. So enough with the slides. Let me actually switch and show you a quick demo of SIMBA. So this is the graphical user interface of SIMBA. The interface of SIMBA is divided into three main tabs. The first one is test bench here. This is where you will be able to run parametric studies and do pre-processing of your project. Then design, this is what we see here, where you will be able to create design, create circuits, create models. And then results, where you will see the waveforms, perform FFTs, and do all sorts of processing. In this project that I have here, we have a collection of design examples, simply to illustrate the capabilities of SIMBA. We have simple converters like this three-phase diode bridge. We have more advanced converter like this 5-level MPC converter, or this resonant LLC converter, or this PMSM drive. The nice thing with SIMBA is you can put side by side the design and the results. So I can run a simulation and very quickly look at the result on the right like this. In SIMBA, everything is about speed and simplicity. So even complex converter, like for instance this 5-level converter that has about 50 switches and maybe 100, 200 nodes, is simulated instantaneously here. Okay. So on the right-hand side here, I have my waveforms, the simulation waveforms. I can put cursor, very simple to use. I can run FFT on the results, and that's it. The interface is very easy, and we try to make it as powerful as possible. So why use SIMBA? Well, there are different reasons that differentiate SIMBA from other tools. The first one will be speed. We worked hard for years to build the best possible solver. SIMBA is extremely fast for all types of converters. You can simulate simple converters with switching transients. You can simulate large converters. You can simulate microgrids. We worked very hard to make the build the best possible solver without any compromise on the accuracy. We have a collection of about more than 100 tests that we run every time for every release to make sure that the solver is robust and accurate for every converters. Then the user experience. We try to have a very simple workflow from the installation to the licensing to using SIMBA to looking and exporting the waveforms that basically doesn't need any training. Even if you never used SIMBA before, you know already how to use it. It's extremely simple to use. We think this is how all the simulation tools should be. We believe that for more advanced studies, the scripting interface is essential. And we wanted from the start with SIMBA to have the best possible scripting experience. So we decided to go with Python, and SIMBA is actually available with the graphical user interface, but also as a Python library that you can download and install independently from the user interface. If you don't know Python, it's awesome. It's a very simple and extremely powerful scripting languages. It's basically like a free MATLAB. as you said. It's actually even better than that. You have libraries for optimization, parametric analysis, machine learning, data visualization, and we have a very simple scripting interface that you can use to run parametric studies, to integrate SIMBA in your workflow, whatever it is. So we think this is extremely useful, and Guillaume will make you a demo in a moment. The roadmap of SIMBA is public and collaborative. It's actually available on GitHub. You can go on our website to get the link to the roadmap. Everything that is actually planned in the roadmap has been requested by user. This is very important to us, since it will help us to make the best useful tool, because you, the user, you know more than us what is useful and what is not in a simulation tool. SIMBA is 100% free for students and professors for teaching and research activities. This is very important for us as well. If you are a student, it's very easy for you to get a license. You just go on our website, you create an account, and you request an academic license. It's extremely simple to get a license if you're a student. Then we have a very simple license model. Basically, with a single license, you can install SIMBA on an unlimited number of computers, and you can distribute calculation or on an unlimited number of cores and computers. We don't have modules for specific features, and we don't charge extra depending on the size of the model that you want to simulate. It's very simple and very easy to understand. So that are for us the main reason to use SIMBA. I wanted to explain very quickly why SIMBA is that fast. First, power electronic simulation is not easy. If you look at any power converters, you have a lot of different time constants. You have time constants on the source, on the loads, you have the control systems, you can have mechanical and thermal time constants. You have events in the control system and the switching events that you need to simulate very carefully. So power electronic simulation is not easy, and building a solver that is fast and reliable, accurate, cannot be done in a day. It takes a long time and a lot of effort to build something like this. And one of the reasons the solver in SIMBA is that fast is because of one of the algorithms that we built that we call predictive time step. To illustrate this, here is an example of MOSFET voltage at turnoff in a forward converter. Basically, every red point that you see is a simulation point. Okay, so at first, we use basically a large time step because the system has a slow dynamic, so there is no need to have a very short time step here. Then SIMBA will be able to predict before it happens the discontinuity event, and that's why we call that predictive time step. Here, when SIMBA is here, it knows that there is a discontinuity event here, and it will reduce the time step to make a point just before the discontinuity event. This is extremely important because it guarantees the time of the event. Then SIMBA will make a very small time step around the discontinuity event to simulate the discontinuity event, sorry. And after that, SIMBA is able to predict what are the time constants of the system, and from that it can calculate what is the optimal time step to use. So we don't waste any calculation. We don't do extra time points that are not used. We always use and do a point where it's required to have one. And with this approach, we can guarantee the accuracy of the simulation without having to do a lot of useless time points. And this is one of the reasons why the solver in SIMBA is that fast. If you are interested to know more about it, you can go on our website, and in the documentation section, there is a page that explains this with way more details. Okay, so now I would like to change to the screen of Guillaume. Guillaume will show you a list of different application examples. Guillaume, I think we can hear you.
Okay, can you hear me? Yeah, yeah, great. Okay, so yeah, thanks, Emmanuel. So today I would like to show you the potential of SIMBA through three application examples. The first one, which shows how a proc converter and its control have been implemented with SIMBA libraries. A second one, which shows how it's easy to compare different topologies of a single-phase inverter in the same SIMBA project. And a last example, we will show how pre-processing computations and SIMBA simulations can be mixed together thanks to the Python API. So let's go with yeah. Sorry. Yeah. So is it better? Yeah. Okay, so sorry for that. So let's go with the first example, which is a phase shift full bridge actually, and so this design has been realized thanks to the libraries of SIMBA, of course, the electrical library, but also the control library to implement this. This control system. So what do we have here? Here, this is the voltage control loop. Here, the current control loop, and here this system, okay, sets the delay between the two switching cells according to the duty cycle reference. So if you want to get some details about this system of the PWM implementation, you can go to SIMBA website, just over here. Sorry, just over here. Yeah, and we have a short documentation in the version history of the public beta 4 here with the new example, and here we've got a short text and figure of this implementation of the phase shift PWM, which can answer to your questions. But let's go back to the simulation and try to display some waveforms. So I'm going to simulate the circuits. So as you can see, it's very fast. And now let's display some waveforms. Okay, so first of all, I'm going to plot the output voltage waveform in order to check the regulation process, for example. And in a second chart, I'm going to display the magnetizing current of the transformer and the primary voltage of the transformer. And I'm going to zoom on these waveforms in order to check typical waveforms of such a converter, which is the phase shift full bridge. You can note here that I didn't sync the two graphs so that I can have different time scales between here time constants, which is linked with the regulation process, and here a time constant, which is linked to the switching scale. So this is quite convenient. So what can we do now? Well, for example, if I want to change the reference value, I can do this to might volts. Now I'm going to launch another simulation, and I'm going to plot the previous results of the simulation. Okay, and I can overlay these results in order, to check the difference between the two voltages. So with this first example, you can see that it's very, very simple and very fast to implement support converter and its advanced control and to get some waveforms. So now let's jump to our second example, which deals with the comparison of different topologies of a single-phase inverter. Okay. Here we are. So this is the first topology, which is a classic two-level topology of a single-phase inverter. This is a neutral point clamped converter, and this is a flying capacitor, okay, in inverter. So let's simulate all these topologies: the classic one, okay, the neutral point clamped, and the flying capacitor. And now I'm going to compare them with their waveforms. So first, I'm going to plot in the first graph the output voltage. So you can recognize here the output voltage of a two-level topology, of two-level topologies, and the other one of the three-level topologies for the neutral point clamped and the flying capacitor. And in the second graph, I'm going to plot the current. And this time, I'm going to overlay these waveforms so that here I can really easily check, the benefits of the multi-level topologies in terms of filtering, output filtering. I can check on these waveforms. This time, I'm going to sync the two both graphs, and I'm going to make a short zoom so that here, yeah, it's amazing. It's very easy to see the difference in terms of current ripple between these two topologies. In yellow, this is two-level topologies. In blue, this is the neutral point clamped, and in green, this is the flying capacitor with an aberrant switching frequency, which is twice. So yeah, that's the powerful SIMBA. It's a good trade-off between simplicity and accuracy. So now I would like to show the third example, which deals with a Python API. Okay, so here I wanted to analyze the influence of the decibels voltage variation. Well, let's imagine that we have to define the decibels voltage value of a three-phase inverter, and we want to keep constant the line-to-line voltage, so that the modulation depth has to be recomputed in order to keep constant this AC voltage. So here, this is a screenshot of the three-phase inverter I previously drew in SIMBA, because it's much easier, okay, to use the SIMBA guide for this schematic, and to load the SIMBA in Python. It's quite simple, just these two packages from the SIMBA module, and then I began my Python script. So here you can see that I computed the difference modulation depth depending on the decibels voltage in order to get the same AC voltage. And here in this second cell, I pick the different elements of the SIMBA circuits that I want to modify. Let's say the DC voltage sources and also the PWM blocks. In the for loop, I set the values of the DC voltage sources and the modulation depth of the PWM block, and then run the simulation and get some results in order to plot them. So here below, you can see the output voltage waveform and the output current. If I zoom on the output voltage, you can see different waveforms for the different DC voltages, and you can see here that the modulation depth adapts in order to keep constant the AC voltage. I can also see the influence on the AC currents in terms of ripple, and so to get more details, here below, this is the spectrum of the output voltage. So as a designer, I can check here the evolution of the spectrum depending on the modulation depth, and for example, find a kind of trade-off for this voltage. So this is typically the kind of workflow, okay, where we can do with the Python API. So with this example, it shows that it's very, very easy and efficient to integrate SIMBA simulations in some custom process or internal tools. Well, thank you, Emmanuel.
I think the sound should be okay now. Just let me know in the chat if you have any issue. So thanks a lot, Guillaume. This is really amazing. By the way, if you have any question on everything that we've shown today, feel free to ask question in the chat in YouTube, directly in YouTube. We wanted also to give you a quick overview on the roadmap of SIMBA, what we are planning for the next release, and and what is our strategy. So again, the roadmap is public and collaborative. You can access it directly on the web. At first, for the maybe 3-4 months, we'll have kind of an aggressive roadmap with monthly major releases. And then probably starting May or June 2021, we'll kind of slow down the release, and we want we have a kind of a long-term vision with many innovative features around machine learning, artificial intelligence, and cloud computing. So we can't wait to develop those features and send that to you to see what you're going to do with that. I also wanted to show you. I see some questions in the chat. I will show you this preview, and then I will go back. We will go back to the questions in the chat. So I wanted to show you a preview of the next version of SIMBA that we are developing. We are going to release it in a couple of weeks. One of the features that was really requested by user is the capability to support C code, to build and write code directly in SIMBA to make a custom controller, basically. So we have a new model that's called C code, that's very easy to use. You select it, you can set the number of inputs and outputs, you can scope directly the input and outputs. And if you want to write or modify the code, you simply click on the edit button here. And directly in SIMBA, you have a code editor and a compiler to compile the code. The way it works is very simple. You have 3 main functions: initialize, that is called once at the beginning of the simulation; calculate outputs, that is called at each time step; and terminate, that is called once at the end of the simulation. This example here is a buck converter with voltage and current feedback loops. We model the dead time of the MOSFET here. The switching frequency is about 100 kilohertz, and the controller is implemented as a C code block with the current and voltage loop coded here. And directly in SIMBA, you can run the simulation. And the way we implemented the C code in SIMBA is to make it as fast as possible. So we don't interpret the code, we compile it with a real compiler. And we can look at the results here. For instance, I look at the output voltage. I can change the reference here. It's unstable. I can change the reference and look how the waveforms are updated. So and if you have any error in the MAL, actually when you compile, it shows an error, and you see here the error message at the line 31. I should add a semicolon. This is C code, and then it will work right away. So I just wanted to show you a quick a sneak peek of the next version of SIMBA with with the C code support. Okay, so thanks again. And before we wrap up, we have a lot of questions. Let me check them. Uh, what kind of modeling language can be used for device modeling, like SPICE or Modelica? Currently, there are two ways to create a model. The first one is with the graphical user interface, and the second one is actually in Python. You can build equivalent model with the SIMBA API in Python. We don't support SPICE or Modelica. Modelica is something I'm interested in. Honestly, I don't have a lot of background with Modelica, but at some point, maybe in a more long term, I will be interested to see if we can do something with Modelica. Can you choose commercial MOSFETs, or do you need to manually set the switch parameters? In the current version, you have to manually set the switch parameters. Probably in the February or March timeframe, we will release a new package with actually a database of semiconductors with thermal data. We don't we're still developing that, so it's not very clear how we will implement it. But very soon we'll have actually a database of semiconductors. We don't have it for now. The roadmap. Yes, sorry, Guillaume, go ahead. Oh, sorry about that. I think we don't hear you.
Yes, sorry. Yeah, we have another question which looks like a little bit the first one about modeling language. The question is about the C code. If we can use Python to create controllers.
Yes. Um, so the short answer is no. We wanted to support C code first because usually people will have the C code implemented in a microcontroller. I know that there is a trend in the industry that wants to use Python to code the microcontroller with something like MicroPython. I actually looked at it over the last weekend. It will be very easy to do actually to support Python in the C code, but right now we don't do that. If there is a need, and if you want to discuss about that, feel free to contact me, and I will be pleased. We can have a 15-minute call to understand a little bit what you want to do, and I will be pleased to know more about it. There is another question. Have you thought about the timeline for discrete time modeling and software in loop testing, embedded coder development? I'm not sure about the question. I don't really understand the question. So right now, I mean, in the next version, we will have C code support. So you will be able to put the same code you put in the microcontroller directly in SIMBA. In the March or April releases, we'll have more model for discrete controller. I hope I have answered the question. If it's not the case, please let me know. Okay. Please let us know if you have any other question. Otherwise, you can check and actually try SIMBA right now. You can go on simba.io, create an account, and start using it right now. If you have any questions, feel free to contact me or Guillaume. We will be pleased to help and pleased to talk with you. Guillaume, is there anything you wanted to add?
Yeah, well, we have a last question. Can we export simulation results, for instance, as a CSV file similar? Well, I can answer to this question. The manual. Well, if you use Python API, it's very easy to export results. So, well, you can prepare all your simulation with the graphical user interface, and then just use the Python API to export your results. That's very simple, as simple as that.
And actually, there is actually an export option directly in SIMBA. You can export here, export a graph directly in PNG or
Oh, yeah,
CSV. So you can
that's right.
also use this to export the data of a waveform. Okay, so I think we can wrap up this webinar. I hope it was interesting, and I hope you will try and like SIMBA. If you have any question, feel free to contact us. We'll be pleased to discuss with you. And that's it. Have a great day, and thanks again to have joining us today. Thank you.